Okay, in this video, we're going to talk about separable differential equations and apply this adjective, this new adjective, separable, to first order differential equations. Remember that a general first order equation is something that looks like, so a first order equation is something that looks like y prime equals f of xy. So perhaps some complicated expression in x and y here. And the complication in f of xy is what makes the subject of solving first order differential equations so difficult, right? You can have very, very complicated things, and this causes the theory to become very, very difficult very, very quickly. On the other hand, so what we very often want to do is narrow down to sort of special cases of f of xy. One special case that separability, this concept of being a separable equation, covers is when f of xy can be written as a product of a function of x and a function of y. You can think of it like you can factor f of xy into a product of these two types of expressions. So a separable first order equation is a special case of the above. It's y prime equals f of x times g of y. Okay, where f and g are some, again, functions of, but now just of x and y respectively. Okay, they're just functions of a single variable. It is definitely not the case that you can always factor a function like f of xy into a product of f of x and g of y. But in this special case, we have techniques that we can bring to bear to solving this kind of differential equation. Okay, so I'm going to talk about it in general, how to solve such functions. And then, of course, we'll do examples. So how to solve separable differential equations? Well, let's start with the equation y prime equals f of x times g of y. And what I'm going to do first is I'm going to bring g of y over to the other side of the equal sign by dividing both sides by g of y. Of course, you should worry because what is g of y after all? It could be 0, right? But let's just put that aside for a second, okay? And so here I've got an equality of functions of x. I mean, I had that above too, but I just want to emphasize this. This side over here is clearly a function of x, right? Some complicated expression involving x. This, though, remember, y here is a dependent variable. It depends on x, the independent variable. So this is also, even though it's got all a bunch of y's and maybe a y prime in there, it's still a function of x also, okay? This is the idea. And if that's the case, then what we're talking about here is one function of x being equal to another function of x. That's what this differential equation is asserting. So what I'm going to do is integrate both sides with respect to the variable x. So this is equal to, this gives me 1 over g of y prime dx is equal to the integral of f of x dx. Okay. Now we're going to do a substitution. This is an interesting move. We're going to let u equal y. If u is y, what is du? Well, it's simply y prime dx. Yeah. This is just a calc 2 move that we're doing, a single variable calculus move that we're doing here. And then we can rewrite that left-hand side using the substitution. We get the integral of 1 over g of u. Remember, u is y is u. And y prime dx becomes our du. So we get this equation. And then we can replace the u that we see here. We can replace the u here with y. We're reverting back. So then we get the integral of 1 over g of y dy is equal to the integral of f of x dx. Okay? So I want you to see where we started. We started here, and where we ended up with is here. And this leads to a kind of symbolic way of thinking about separable differential equations, and I want to sort of share that with you here. This is the kind of thing that gets the goat of mathematicians who really like rigor. Okay, and I like rigor; it's great. But I so when I explain in this way, please understand that I'm committing a bit of a mathematical sin of yeah. Anyway, so I'm going to rewrite y prime as dy dx. And we have, of course, f of x times g of y. And now the idea here is that I'm going to separate garbage that involves x only. I'm going to put that on one side of the equal sign and put garbage that involves y only on the other side of the equal sign. Right? It's like the equal sign is like the Berlin Wall that separates the East Germans from the West Germans. And of course, there's other instances of segregation that we all know about. But that's sort of what I'm doing. Okay, I'm segregating the stuff involving x. I'm separating that from the stuff that involves y. And the wall here, the barrier, is this equal sign here. Now, what are the things that involve x in this equation? Well, there's f of x, clearly. But now here's the part that's going to make people mad. There's also this dx here. And the way that I'm going to think of it is that it's in the denominator of dy dx. Okay? This is where people get mad. What are the parts involving y? Well, that's g of y and dy. Okay? So to do this segregation move, what I'm going to do is divide both sides by g of y and multiply both sides by dx. If I do that, I get dy over g of y is equal to f of x dx. All right. Now I've got this equation here, and now here is another place where people are going to freak out. This side is a function, is an expression involving y, which whatever, and this side here is the function expression involving x. Okay, here's the bold move I'm going to make. I'm going to integrate both sides. Okay, this side I'm integrating with respect to y. This side I'm integrating with respect to x. And I guess I'm claiming that this is the right way of going about doing this. The thing is, though, look at it. Look at that, okay? And look at this. Those two things are the same. These are the same. And this is the sort of right way of thinking about it. This is the kind of wrong way of thinking about it, but it leads to the same spot, okay? Okay. So, but you get the idea, okay? You treat temporarily dy dx as a fraction, and then you segregate the variables. You put all the stuff involving x on one side, all the stuff involving y, typographically involving x, typographically involving y on the other side, and then you integrate both sides. That's the idea. And that's how you go about solving a separable differential equation. Let's do an example. So for this example, let's do something very simple, like y prime equals x over y. Okay? So I claim, and I'm right, that this is a separable differential equation, because we can write this as x times 1 over y. And what's playing the role of our f of x in the general theory is this, and what's playing the role of our g of y is that. Okay? Now I'm going to separate the variables. I'm going to use the typographical, not so rigorous way of doing things. So I have dy dx is equal to x over y. I'm going to move the stuff involving y onto one side, move the stuff involving x to the other. So I get that after doing that, I get y dy is equal to x dx. And then I integrate both sides. Okay? So integrating this side here, I get 1/2 y squared plus c. I'm going to reserve the plus c for the other integral, okay? And then this side I get 1/2 x squared, and that's where I'm going to write the plus c. I would get a additive constant of integration from the other side, but I'm just going to glom them together into a single additive constant of integration on that side. Okay. Next thing I'm going to do is I'm going to multiply both sides by 2. I'm now in the process of trying to solve for y. So that's what I'm going to do next. Y squared is equal to, so 2 times this is x squared plus 2c, but 2 times c is the same thing as c. Okay. And then I'm going to take the square root of both sides. Now, this is where a lot of students make a small mistake. The mistake here is just writing y is equal to the square root of x squared plus c. This is incorrect. And it comes from the fact that you think that the square root of y squared is equal to y. This is false, right? The problem with this equation here is that if y is negative, then y squared, the square root of y squared is not y, it's negative y. Let me say that again, just because I know this is a point of confusion for a lot of people. The square root of y squared is not y. The square root of y squared is in fact the absolute value of y. So this is false as written. Here is the truth. This is a true statement now. And the reason is because if y is negative, then the square root of y squared, that is to say this side, is not y. The square root of negative 5 squared is not negative 5. It's 5. And so, yeah, this here is the truth. And so in particular, when we took the square root of both sides of this equation in our problem, we needed this. Now, how can the absolute value of y be equal to a thing? That's if y is equal to plus or minus the thing. And here is the general solution. Okay. So for each choice of c, in fact, we have 2 solutions. We have the plus square root of x squared plus c and the negative square root of x squared plus c. Okay, those are both solutions to this differential equation, which, by the way, you can always check. Just put in this expression back into the original equation here, this one, put it back in, and just check that this really is y prime, right? Okay, all right, very good. How about this example? One more example. Actually, you know what? Let's do the next example in the next video. How about that? We'll do in 5.2 more examples and maybe solve some initial value problems as well. Okay, see you in the next one.